Welcome to G Fun Facts Online. Imagine holding a silicon chip, the kind that powers your smartphone. Now imagine that inside that chip, individual atoms are whispering to each other, communicating across relatively vast distances on the atomic scale. This isn't science fiction. It's a reality recently achieved by quantum engineers, a phenomenon they've nicknamed silicon chatter. This unprecedented breakthrough has shattered a fundamental barrier to building large-scale quantum computers, suggesting that the heart of the next technological revolution might just beat within the familiar confines of a silicon chip. Today, we're diving deep into how scientists taught atoms to talk, and why this could be the most important conversation of the 21st century. The global race to build a quantum computer has explored a menagerie of exotic hardware. We've seen superconducting circuits, trapped ions, photons, and even diamonds with tiny defects. Each has its pros and cons. Superconducting qubits, for example, have been built into processors with dozens of qubits, but they are physically large and very sensitive to noise. Trapped ions boast incredibly long stability, but scaling them up to the millions needed is an immense engineering hurdle. Amid this diverse landscape, silicon has long been the dark horse, the one with immense, untapped potential. The primary reason is its ubiquity. For over half a century, the relentless march of Moore's law has driven the miniaturization of silicon transistors down to the nanometer scale. This has created a global, multi-trillion-dollar manufacturing ecosystem capable of producing billions of devices with atomic-scale precision. If quantum bits or qubits could be built using this same material, it could provide a shortcut to manufacturing quantum processors with the millions of qubits necessary for truly powerful, fault-tolerant computation. It's about leveraging the most mature manufacturing technology on the planet, but it's not just about manufacturability. Silicon offers a uniquely quiet environment for quantum information. You see, natural silicon contains about 4.7% of an isotope called silicon-29. This isotope has a nuclear spin, which creates a kind of magnetic chatter that can disrupt the fragile quantum states of a qubit. The solution? Engineer isotopically pure silicon-28, which has no nuclear spin. This creates an almost perfect, noise-free vacuum for qubits to exist within. This pristine environment has led to astonishingly long coherence times, the duration a qubit can maintain its quantum state. Some nuclear spin qubits in silicon have maintained their information for over 30 seconds. In the quantum realm, where operations happen in nanoseconds, 30 seconds is an absolute eternity. This visionary path for silicon quantum computing was first laid out in 1998 by physicist Bruce Kane. His audacious proposal was to use individual phosphorus atoms embedded in a pure silicon crystal as qubits. The quantum information would be encoded in the nuclear spin of the phosphorus atom, a property that is exceptionally well isolated from its surroundings, hence the long coherence times. But to make these qubits compute, they had to interact. Kane proposed using the phosphorus atom's outer electron as an intermediary. By applying voltages to tiny metallic gates on the chip's surface, the electrons of adjacent atoms could be made to interact, thereby entangling the nuclear spin qubits. It was an elegant plan, but it presented immense fabrication challenges. For over 2 decades, researchers have been systematically overcoming these challenges, and this recent silicon chatter breakthrough is the spectacular vindication of that long-term vision. This brings us to the central challenge that the team at the University of New South Wales, led by Professor Andrea Morello, finally solved. It's the trade-off between isolation and interaction. The nuclear spins of phosphorus atoms are fantastic for storing quantum information precisely because they're so isolated. But this very isolation makes them reluctant to talk to each other. Their natural interaction is so weak it would take forever to perform a single calculation. Previous attempts tried to get these nuclear qubits to interact by having them share a single electron. The idea was that this shared electron, which can be spread out in space like a quantum wave, could be influenced by both nuclei, creating a link. But this approach had a critical flaw. it didn't scale. Cramming more nuclei around a single electron made it impossible to control each one individually. The signals would become hopelessly muddled, like too many people shouting on the same radio frequency. The UNSW team's breakthrough was to devise a completely new way for the nuclei to communicate. Instead of sharing one electron, each phosphorus nucleus in their device had its own dedicated electron. The talk between the nuclei was then mediated by a controllable interaction between these two electrons. As lead author Dr. Holly Stemp elegantly explains it, it's like they gave each person in their soundproof room their own telephone to communicate with other rooms. This electronic telephone is a manifestation of a fundamental quantum mechanical effect known as the exchange interaction. It arises from something called the Pauli exclusion principle, which dictates that two identical particles like electrons cannot occupy the same quantum state simultaneously. When the researchers apply precise voltages to nanoscale gates on the chip, they can gently nudge the wave functions of the two electrons until they overlap. This overlap activates the exchange interaction, and its strength can be tuned with exquisite precision by the gate voltages. This controllable interaction is the key that allows the electrons to act as a switchable link between the nuclear spin qubits. The team used this electron-mediated link to implement a crucial quantum operation known as a controlled Z or CZ gate. A CZ gate is a fundamental two-qubit logic gate that creates entanglement. It works by flipping the quantum phase of one qubit, but only if a second control qubit is in a specific state. In this landmark experiment, the team performed a CZ gate that entangled the two phosphorus nuclear spins in about 2 microseconds, a speed that is well within the requirements for practical quantum computing. What's even more elegant is that this is a geometric gate. In a conventional or dynamical gate, the outcome depends on the precise duration and strength of the control pulses. But a geometric gate depends only on the path the quantum state takes through its abstract parameter space, not the time it takes. This makes geometric gates inherently more robust against noise and control errors, providing an extra layer of protection for the delicate quantum information. This achievement is a culmination of over a decade of pioneering work by Professor Morello's group, who have now added the crucial missing piece of the puzzle: a scalable method for long-range, high-fidelity 2-qubit gates. The device at the heart of this breakthrough is a true marvel of nanoengineering. The process starts with a slab of ultra-pure, isotopically enriched silicon-28. Using a technique that combines scanning tunneling microscopy and molecular beam epitaxy, individual phosphorus atoms are implanted into the silicon crystal lattice with near-atomic precision. In this specific experiment, 2 phosphorus atoms were placed approximately 20 nanometers apart. Above the silicon, a thin insulating layer of silicon dioxide is grown, and on top of that, a series of metallic gate electrodes are patterned. These gates, which are themselves nanoscale structures, act like a sophisticated switchboard. By tuning the voltages on these gates, the researchers can massage the shape and extent of the electron wave functions, turning the exchange interaction between them on and off at will. The entire chip is then cooled down in a dilution refrigerator to temperatures of just a few millikelvin, a tiny fraction of a degree above absolute zero. This extreme cold is necessary to freeze out thermal vibrations and other sources of environmental noise that would otherwise instantly destroy the fragile quantum states. The 20 nanometer distance between the qubits is not arbitrary. It's a technologically significant scale because it's comparable to the size of transistors in the chips that power our modern world. This is what makes it a true technological breakthrough. By proving that you can make the most stable, isolated quantum objects communicate at the same scale as existing electronic devices, the UNSW team has shown that the manufacturing processes of the trillion-dollar semiconductor industry can be adapted to build quantum computers. The UNSW team's electron-mediated approach is a landmark, but it's not the only strategy being pursued to solve the quantum communication challenge. One alternative is the quantum bus, or qubit shuttle. Here, the idea is to physically move an electron, and the quantum information encoded in its spin from one part of the chip to another. Researchers have developed a quantum bus that can transport an electron over 560 nanometers by creating a potential wave on which the electron can surf, controlled by a series of timed voltage pulses. The goal is to extend this to about 10 micrometers, enough to bridge different processing modules on a single chip. Another powerful technique involves using microwave photons as messengers. In this scheme, two distinct qubits are coupled to a common superconducting resonator, a tiny on-chip cavity for microwave photons. By tuning the qubits into and out of resonance with the cavity, they can exchange a virtual photon, which mediates an interaction between them. A team at Princeton University has used this to entangle two silicon spin qubits, separated by about half a centimeter. Finally, looking even further ahead, silicon photonics is emerging as a compelling technology. Silicon is also a great material for guiding light. Researchers are developing integrated circuits that can generate and manipulate single photons. One approach involves creating T-centers, a specific type of optical defect in silicon that can act as a spin-photon interface. These T-centers have a spin that can be used as a qubit, and they can emit photons that are entangled with that spin. These photons could then be sent through on-chip waveguides, or even off-chip optical fibers to link distant qubits, potentially forming the basis of a future quantum internet. The silicon chatter breakthrough is monumental, but the road to a large-scale, fault-tolerant silicon quantum computer is still long. First is the scourge of decoherence. While silicon-28 is quiet, it's not perfectly silent. Spin qubits in silicon are particularly susceptible to charge noise, fluctuations in electric fields caused by tiny defects at the interface between the silicon and the silicon dioxide layer. These fluctuations can disrupt the very exchange interaction used for the two-qubit gates, introducing errors. Then there are the fabrication challenges. While leveraging the semiconductor industry is a huge advantage, building a quantum processor still requires a level of control that pushes the boundaries of even the most advanced techniques. Placing millions of donor atoms with precision and ensuring every quantum dot is uniform is incredibly difficult. Even tiny variations can lead to a few poorly performing qubits that can cripple the entire device. There is also the challenge of the supply chain for isotopically pure silicon-28. While small quantities are available for research, scaling up to industrial production is a significant undertaking. Next is the tyranny of numbers, often called the wiring bottleneck. A quantum computer with millions of qubits would, in a conventional design, require millions of control lines running from room temperature down to the cryogenic chip, which is simply not feasible. To overcome this, researchers are developing cryogenic CMOS, or cryo-CMOS, circuits that can operate at the same low temperatures as the qubits. This would allow control electronics to be integrated directly onto the quantum chip, dramatically reducing the wiring. Finally, and most critically, any useful quantum computer will need to be fault-tolerant, employing quantum error correction, or QEC. QEC works by encoding the information of a single logical qubit across many physical qubits. By constantly measuring and correcting errors on the physical qubits, the logical information is protected. The surface code is a leading candidate for this, as it only requires nearest neighbor interactions, which is a good fit for a 2D chip architecture. But it's a massive undertaking, requiring a huge number of high-quality physical qubits and fast, high-fidelity operations across the entire chip. The demonstration of silicon chatter has reinvigorated the global quantum effort by providing a credible, manufacturable path to scaling up to the millions of qubits needed for a universal, fault-tolerant quantum computer. The journey is far from over, but the roadmap is finally becoming clear. In the near term, we'll see researchers focus on scaling from 2 qubits to larger, multi-qubit arrays, and demonstrating the basic elements of quantum error correction. As these systems grow to a few hundred or a few thousand qubits, they will unlock new opportunities. Even these noisy intermediate-scale machines could tackle problems currently intractable for our best supercomputers. In medicine, they could accelerate drug discovery by simulating how molecules interact with proteins. In materials science, they could help design new catalysts for green energy or novel materials for better batteries and solar cells. Looking further ahead, a large-scale, fault-tolerant silicon quantum computer would be truly transformative. It would enable the breaking of current encryption standards, forcing us to develop new, quantum-resistant cryptography. It could fuel breakthroughs in artificial intelligence, optimize global financial markets, and give us a tool to probe the deepest mysteries of the universe. The story of Silicon Chatter is a testament to long-term scientific vision and relentless engineering. The whispers of atoms talking to each other on a silicon chip today are the prelude to a roar of technological change that will redefine our future. It seems more and more likely that the next great chapter of computing will be written in silicon once again.